The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I've been working on this topic for about 8 years now, and there's been a whole lot of students. Many of them are actually mentioned here at the bottom, and some of them are actually here in the room today. So that's exciting because they're the really great ones. They're the ones that do all the hard work. And I want to acknowledge right up front Ken Hover. And the reason why is that Ken originally he has got a brilliant mind, got a very interesting guy. And he had this idea many years ago to investigate an air meter. Can we do more with a pressure meter? And I was really lucky, really lucky. I was actually a PhD student of Kevin Folliard at UT Austin. And Kevin would come back to us every year, and he would tell us about this. And how Kevin knows is that he spent the summer as an undergraduate researcher working for Ken Hover. I mean, what a dream team there, right? I mean, and they actually worked together. And Kevin, when he was there, would tell me stories about how Ken was putting, like, tennis balls inside pressure meters and running it and doing all kinds of stuff with just mixes with fly ash that wouldn't set, all kinds of just crazy ideas. And as a young student to hear all that, that's just inspiring. So I wouldn't be here today, and this work wouldn't be here without those two folks. I also have to thank the folks that funded the early research on it, and currently there is a research project going on. It's a pool fund study by 16 different groups, all to investigate some of the stuff that I'm going to talk to you about today. So we're going to talk about some basics of air and train concrete. We're going to talk about the super air meter, and then we're going to talk about the future. So de-icer salts, that's what we're here about, to talk about today. That's what brings us all together. And the use of de-icer salts are critical for the safety of our traveling public, right? We don't want families sliding off the road, right? We need to take care of that ice, okay? And the highway agencies are becoming much more aggressive, using different de-icers, using pre-treatments, using all kinds of actual techniques to try to make our roads more safe. De-icer salts has been talked about before, can exasperate freeze-thaw damage of concrete, and this isn't going away. Okay, we've got to figure out how to handle it. We've got to figure out how to deal with it. We're going to talk about freeze-thaw today. And when we talk about freeze-thaw, it's all about the freeze-thaw triforce. It's all about three things. Okay? For freeze-thaw durable concrete, you have to have durable aggregates. You have to have high-quality paste. And you have to have a high-quality air void system. But I'm only going to be talking about the air void system today. Everything I'm talking about cannot help you if you're next door in the decracking seminar. I can't help those folks. Okay? Air doesn't help those folks. Well, maybe a little bit, but not really. I can't help you if someone adds way more water to the concrete than they're supposed to. Can't help you. Can't help you. But air void systems, that's going to be helpful today. So why the heck do we add air to concrete? Because it's not very strong, right? Well, these air bubbles happen to be the key to the freeze-thaw resistance of our concrete. This is really important, ladies and gentlemen. Air volume is not necessarily equal to freeze-thaw performance. It's not about the volume. It's about the size distribution of the bubbles. Okay? And smaller bubbles are much more effective in providing freeze-thaw resistance than larger bubbles. And let's talk about why. So I've got two air void systems, one on the left, one on the right. Both of them have the same volume of air. But we would much rather have the air void system on the right. We'd much rather have the small, well-distributed bubbles. And why is that? Well, if I'm a water molecule and I'm in this paste and I start to freeze, I just want to escape to a boundary. Okay? And if I can provide much more boundaries inside, it's going to provide much more protection. And this concept is called the protected paste concept. Okay? And we can see we get much more protection out of the air void systems on the right than we do out of the air void system on the left. So what's that mean? We want small, well-distributed air bubbles. And it's about distribution, not always about volume. So I'm going to show how do we get this information. Well, the only way to get it now is through a hardened air void analysis. You have to cut concrete. You have to polish concrete. You have to go through it. And every time you actually go through this line, you have to hit a button. When you enter a button, or when you actually enter a bubble, you have to release the button when you actually leave the bubble, and it takes a long time. It's not very fun. Okay, but out of that, you get this magical number called the spacing factor. Spacing factor developed by T.C. Powers, okay? And what Powers did, he did some really cool stuff using 2D stereology to take the 3D air void system and turn it into an equivalent kind of synthetic air void, so kind of a supplementary air void system to the real 3D distributions. This is like an idealized concrete or idealized air void system. So it's average size voids at an average spacing inside the paste. And it takes twice this number, twice the spacing factor number is the diagonal. If you didn't understand anything I just said, it's okay, okay? Because the desired value, what you're after, what everyone's shooting for, is a number that's less than 0.008. That's the magic spacing factor number. So why the heck can't we just use air instead of or total air? Why do we need to care about air void size distribution? Well, let's look at stuff like this. Here we've got air content plotted versus spacing factor. And this is a mixture that just has air entrainer in it, just air entrainer. And as you add more and more air, spacing factor goes down, goes down, goes down. When you get about 5.5% air in the concrete, you would hit your magic 0.008. People would be happy. Okay, let's show another mixture. Now, this is a mixture. This is a blend. This is an air entrainer and a high-range water reducer. Okay, this is commonly used. High-range water reducers are commonly used in our industry today, and they don't all do this, but some do. Okay. And we can see there's a big offset in the line. And to actually get a spacing factor of 0.008, you need something like 7.5% air content. So how do you specify this? If you're an owner, and now we're telling you that depending on the admixture combinations, you may need different volumes of air. Okay, that's tough, and this is why I call this the yikes graph. This is the oh my gosh. This is kind of interesting. Okay, so that's neat. That's air. Let's talk about, let's introduce a little bit more data. So again, I've got air content down here at the bottom. I've got spacing factor over here. And I've got some data points that are filled. And I have some data points that are open. And anytime it's an open data point, that means it failed the freeze-thaw test, C666 test. That means durability factor was less than 70. Okay? So again, if this suggests that if I get 3.5% air in my concrete, I'm going to be good. These are mixtures with just air entrainers in them. Okay? Let's look at some mixtures that are a little different. Let's look at some mixtures that happen to be, these are combinations of 5 different commercial high-range water reducers and common air entraining agents. And we can see there's an offset in the actual line. And we notice we have all kinds of open symbols. These are kind of interesting. These 7% air is enough to meet every single specification in North America as far as total air content. Yet we're showing and saying that at least in this very aggressive C666 test that we're showing that they would not pass. Okay? So why does this happen? Why is this going on? Well, if we go back to the hardened air void analysis, and instead of using the spacing factor, if we go in and look at the true distribution of the bubbles, okay? And I'm showing 2 bubble distributions. One's just a straight air entrainer here, and one is the air entrainer and the high-range water reducer. And it's on the x-axis is the chord size. If you do a linear traverse, you can truly measure the individual chord sizes. And you compare it to frequency, or how often they occur. So if you integrate underneath these curves, they integrate to 100%. Right? That's what they do. I mean, we can see here that when you add air from mixtures with just an air entrainer, you get a lot of small voids. That's good. That's good. It's good. And in this system doesn't happen in all of them, and I need to stress that. This does not happen in all of these products, but in some, okay, this system seems to have a lot more voids on the larger side. So when I get a certain volume of air, some more of those are larger voids than in this scenario. So, in summary, it's common to require a certain volume of air in concrete in order to get freeze-thaw durability. The volume of air does not necessarily equal air void system quality. And although we could run a hardened air void analysis and figure all that out, that's not really practical. Not really practical. So what do we need? Well, we need a test that can quantify the air void systems quickly in fresh concrete. We need it to investigate a significant sample size. It needs to be economical, and it needs to be field ready. And I'm going to talk about the super air meter, or we call it the SAM for short. And what we did is we modified a typical pressure meter so it can hold higher pressures. And we've actually replaced the dial gauge with a digital one. The test is going to take between 8 to 10 minutes to run, depending how experienced you are, right? And my students can do it in 8 or less, okay? And this is what it looks like, okay? It looks like a typical pressure meter, but it's got 6 clamps around the outside. Why? Because we're going to higher pressures. It's got a digital gauge on top, and this digital gauge is really important. The gauge tells the operator how to run the test. And then it watches the operator run the test. And if it's run incorrectly, it voids the test. Okay? And then it does all the calculations for you and gives you 2 numbers, air volume, and then something called the SAM number. And it's orange on purpose. Go Cowboys. Okay? So how does it work? Well, you fill the bowl typical way we always do when we run a typical air test. Put the lid on it. Add the water through the petcocks, okay? And we're going to be talking about what's going on in the top chamber, what's going on in the bottom chamber. The top chamber, that's just got air in it, okay? The bottom chamber, that's where your concrete goes. There's the petcocks. There's the water, okay? If you look at this graph, we have time plotted down here. We have pressure plotted over here. I'm showing the pressure in the top chamber, the pressure in the bottom chamber. We go up to about 14.5 psi. Hit the lever, smack it with the mallet, and this is what you commonly do when you run an air test. This is it. This is where you stop. With the super air meter, you don't stop. You leave the petcocks closed, and you pressure it again. This time you pressurize the top chamber up to 30 psi. You hit the lever again, and you smack it. Then you pressure it up to 45 psi. Hit the lever, smack it again, and you get a curve. Okay? You get a curve. Now, you release the petcocks. Be careful not to spray anybody, okay, unless you don't like them. And then you do it again. And you compare the first curve to the second curve. And if you look closely, you'll notice they're not quite the same, okay? And that's the differences between these curves is how we calculate the SAM number, how we actually find out what it is. So you'd say, how does it work? Well, the SAM number is going to correlate to air void size distribution. I'm going to prove that to you coming up. And the meter's also going to measure air volume, okay? You still get air volume. You're going to get this other number, though, the SAM. So how can we prove it? We made a lot of different concrete mixtures, different air entrainants, AEAs, different combinations, air entrainants, agents, and high-range water reducers, different water cement ratios, different slumps, different air contents. When we did hardened air void analysis on every single one of them, okay? It's about 95 different mixtures that went into this data set. And the values were all compared to the SAM number. And this is the most important plot of my entire presentation. This is SAM number down here. This is spacing factor over here. And this is a bunch of data. And we see when a SAM number is 0.2, it does a good job of segmenting the data into this is the agreement regions, and this is the didn't quite agree region. And there's about a 93% agreement when you segment the data between yes and no. So when your SAM number is low, your spacing factor is low, and that's the yes. Yes, that's good. When your SAM number is high, your spacing factor is high, and that's the no. That's not as good. And that's interesting. That's about 95 different lab data mixtures. Okay. Now then we went out and did field data. This is about 80 different field mixes. And again, we see it segments the data in the exact same way. There's 0.2, 008, yes, no, breaks it up. That's pretty cool. So this is work that's been done by FHWA Turner Fairbanks Labs, okay, the super air meter. This is what they got. Again, breaks the data up very nicely. They've got like an 85% agreement, I think. Okay, so it's in the ballpark. It's close. And the cool thing is if you put all the data together, it's all agreeing. It's all suggesting similar things. Okay? That as your SAM number goes up, your spacing factor goes up as well. Okay? And 0.2 does a pretty good job of segmenting the data. So the great thing about this test is that you can take this yikes graph that how do you specify for this? How do you handle this with air volume? Remember that's air volume on the bottom? That's spacing factor over here. And when you use the SAM number instead, look, it all smashes down here right at 0.2. It does a good job. It helps segment out the data. It helps make a decision whether this is an air void system that you want or that you don't want. So people love freeze-thaw testing, and we're just getting started on that. That freeze-thaw tests take about 3.5 months to run, so they take a long time. But we have SAM number over here, durability factor over here, and here's 0.2. Okay, and you can see this is great, 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 and then you kind of fall off the hill of death if anyone's run a bunch of bunch of these tests. There's a hill of death right here. You just can't see it because everyone dies once they go there. Okay, but that's you can laugh. You know, that's allowed, right? Okay, great. Only at the funny jokes, right? So the SAM number of 0.2 seems to correspond to the spacing factor of 008. Over 90% of the data is correctly separated with this limit, and the SAM number seems to correlate with some C666 testing. Don't worry, a bunch more is coming. So how consistent is it? Well, we ran 95 different mixtures with 2 meters, okay, and compared them head to head. We're going to compare air contents and SAM numbers. And there are some tweaks that have been made to make an air test better, I guess, make a typical air volume test a bit better. And once you do that, if you compare SAM number 1 versus SAM number 2, this is like just the air content from the first SAM versus the air content from the second SAM, the mean difference is 0. And it's very, very tight. It does a good job, okay? But when you compare SAM number from meter 1 and SAM number from meter 2, again, the mean difference is 0. There's a bit more spread in the data, but again, not so bad. It's given us a lot of data that we never had before. So I know you're asking about this. How does this work? How does it really work? What is the science behind what's going on here? We'll start talking about that. And there's still work ongoing. We're going to take some bottles, okay, about 3 inches tall, about 2 inches wide, and we're going to fill them full of cement paste, okay? They're air-entrained cement paste. We're going to turn the bottles on the side. We're going to actually add a straw to the top and a bit of water. We're going to turn them on their side. So this is the bottle. They're turned on their side, and some bubbles are going to rise up and get caught on the surface. And we're going to be able to look at them with a stereo microscope, okay? And then we've got this air pump over here that we can pressurize the system, and we can look at the bubbles. This is really important. These bubbles are not inside cement paste. These bubbles are in the bleed water, right? They've risen up, and they're in the bleed water, okay? That's what we're going to be looking at. So here's a typical air void system. Here's atmospheric pressure. Let's start looking at what happens when we go to 1 pressure. Things move around a bit. Here's 2. We can notice some of these bubbles don't look as happy. We go to 3. Does anyone notice there's less bubbles? We go to 4, 5, 6. Holy cow. Where are the bubbles going? Well, let's go back to atmospheric pressure. When you go back to atmospheric pressure, a couple bubbles come back. Some of these bubbles come back. It didn't dissolve. What's going on? As you increase the pressure, you're dissolving bubbles. Okay? You're dissolving it. Let's talk more about that. And this is what it used to look like, and this is what it looked like after you brought it back to atmospheric pressure. Before, after. So as you increase the pressure, you're actually dissolving the small bubbles into solution. Okay? So why is this happening? Well, believe it or not, bubbles that are small have a higher pressure inside of them than bubbles that are large. That's described by this equation, Laplace-Young equation. The air pressure inside a bubble is a function of the pressure of the fluid around it and the diameter. So this means, since diameter is in the denominator, as bubbles get small, this internal pressure goes up. If you don't follow me, let's look at a plot. Big bubbles, this is my pressure, not much above atmospheric. Small bubbles, higher than atmospheric pressure. Does that make sense to everybody? Smaller bubbles have a little bit higher pressure in them. Okay? So as you start to increase the pressure, okay, when air gets to a certain pressure, it will dissolve. This is Henry's law. Okay? Henry's law. It says that, and it's usually used for lakes and streams and people worried about pollution, stuff like that. Okay? But it says that when air gets to a certain pressure, any gas gets to a certain pressure, it will dissolve and go into solution. Be gone, basically. So that's kind of what's going on with these small bubbles. So we did a couple additional experiments where we actually tracked individual bubbles every 5 psi in pressure. We went from atmospheric pressure up to 35 psi, followed individual bubbles, and this is kind of interesting. I got 2 systems here. System on the left is what I'm going to call the spaced bubbles, the bubbles that are a little far apart. The bubbles that you'd have would have a poor spacing factor. The bubbles on the right is what I call the close bubbles, bubbles that are a little more closer to one another. Size distribution is very similar, mixture is the same, air content's the same. Some are close together, some are spaced apart. As I increase the pressure up to 35 psi, these bubbles that are far apart, where are they? They've dissolved. Okay? But look here. The bubbles that are close, some of them are still around. Interesting. When I go back to atmospheric pressure, not very many of these bubbles come back, but a whole bunch of these bubbles do. When you bring the bubbles closer together, they perform differently under pressure than if they're further apart. And that, in my opinion, is how fundamentally the superaerometer works. Let's look at it graphically. I'm showing the space bubbles, bubbles far apart, versus close bubbles. I picked these bubbles on purpose because they originally were about the same diameter. And as you increase the pressure, these space bubbles go down and down and down and down, and then they dissolve. Look at the bubbles that are close together. Sure, they go down in size, but they don't ever dissolve. And once you decrease the pressure, they come back. I think this phenomenon is exactly why the superaerometer works. Okay, we're working harder on it now. So the close bubbles respond differently to pressure than the space bubbles. The close bubbles does not dissolve at the same pressure as the space bubbles. Those are two true statements. Okay, so what are possible mechanisms? And we can spend the whole rest of the day talking about this. And bubbles respond differently to pressure when they are close. That's a possibility. It also could be that the fluid around a bubble may become saturated in air, maybe. And this may make it harder for the close bubbles to dissolve in the solution. Let's just say the famous words, more research is needed, right? It's our academic mantra, right? So why is the SAM useful? Let's get back to reality here. Why is the SAM useful? Air volume is no longer enough to evaluate some modern concrete mixtures. And the SAM number could be a tool to investigate the air void systems in the fresh concrete. It could be looking at admixture combinations, cement types, SCMs, sand gradations, haul times, consolidation from pavers, pumping, all different types of mixtures. The list could go on and on and on and on. So what else have we done? Well, the good news is there's an AASHTO provisional test method that's been approved over the SAM number, or over the SAM. That's great. And the SAM is currently being used in 22 different states right now. So that's also pretty awesome. So how can you guys help? Well, you can tell someone else about the superaerometer. You can try the superaerometer for yourself. And if you do, please share your data. Send a cylinder. We'll do the hardened air void analysis. We do it all the time. Okay? We're really good at it. So in conclusion, air volume is sometimes not enough to determine the air void system quality in modern concretes. And the air void size distribution is much more useful. A novel testing device was shown that they can measure the air void volume and size distribution in the fresh concrete. And the SAM number of 0.20 seems to correspond to a spacing factor of 0.008. And over 90% of the lab and field data correctly was separated by this limit. So the SAM number also seems to correlate well with the limited freeze-thaw testing. Remember, it's all about the freeze-thaw Triforce. And I only talked about one leg. I only talked about air void systems. Okay? Can't help with aggregates. Can't help with paste quality. Superaerometer.com is where you can find out more information about it.